different direction. Okay. So, Team Spencer Kennedy, you can say hi to Jared and Zain. Or just oh. And if you do not hear Team Spencer and Kennedy, please type in the chat room. If I do not see any text in chat room, I assume that you're hearing well. Okay. I will, yeah. I'll put camera on myself, not because I like seeing myself, but while going through lectures and if you go through discussions, I'll refocus. Okay. Okay, so I do not know what to speak for. It should be number 8. What to talk for 50 minutes. The content of today's meeting is very well deliverable in 20 minutes. So I will try my best to just expand. So in some sense, we are almost done, and the order is swapped from previous year, but you already did postulates, and before we go to the next chapter, there is one more piece of information. In some sense, it will be third way to predict future. It will be how to, we already know how to connect slice of Schroedinger equation solution to real world, to observables. And now we do need to discuss how to find solution, how to find the slice of Schroedinger equation at any time. Okay, so here is the little homework. If one can do it in 10 minutes, and I think Friday is adequate, but if you think it is super hard, let me know, we can expand it. The class is by humans for humans, so there is no super pressure, and it goes back through a couple of lectures ago, so if you did well in with trigonometry, or if you can find these equations in online, you'll do this traveling waves, and this free acceleration, it is just stuff that some of us were doing in high school. Just checking that we are on the same page. So what we are going to get today, these equations in white boxes are kind of left traces. Interesting. I will not answer. Left traces in our brains. So the first one is equation coming from Feynman past integral. So if you have slice of wave function in the past, then we compose evolution operator with exponential total energy and practicing accumulation of phase along the microscopical trajectory for each point of space, and then we arrive to the slice of wave function at final time. I'm very pleased to see you guys taking notes. My heart is melting. If you would do book, like writing a book, textbook, instead of taking notes, you may just put a note. See equation 4 pages before, because we already went through it. Okay, so this one is very correct philosophically and mathematically, but it is very unpractical. you cannot be efficient with, well, I cannot be efficient with this equation. The second one is either Taylor series expansion of this exponential, this one leading zeros in first term, right, for short time, or one can obtain the same equation just by manipulating this Schroedinger equation. So going from near past to near future. So slice of the wave function in the past, slice of the wave function in the future that is offset by delta t. And the equation that we are going to derive, go over today, starts from, it has two lines. So, and if you do have wave function of the past, let's say at time 0, we convert wave function into a set of discrete numbers that will give names, expansion coefficients, and then we plug these discrete numbers into general solution that is composed of all eigenstates of time independent Schroedinger equations and exponentials with eigenenergies that come from time independent Schroedinger equation. So basically, we combine three components: the expansion coefficients, eigenfunctions, and eigenenergies, and they will give wave function in any point of the future. This is two lines instead of one, like in previous, but this is mostly practical. And this will work either by computational manipulations or by pen and paper solution for some problems. So it is, if you're taking differential equations, there is no science here. It's just one of the standard methods to solve simple differential equations. And this way is quite productive. So we will practice it several times through the course. So last time, and please speak or type if you are on the remote connection, if something is, if you go too slow or too quick. So Friday you were presenting, and last Wednesday we discussed time independent Schroedinger equation, right? So many solutions, many eigenenergies, many eigenfunctions. And if they're good functions, they obey this orthogonality. So multiplying them by each other, you give either 0 or 1. So if I consider myself like a kid in a sandbox, then here are my little toys, building blocks. So I take them and construct something useful, at least for myself, out of them. So in narrow sense, time independent Schroedinger equation also tells us something about stationary states. But in more general way, it is not goal, but it's equation that produces building blocks to solve more general time dependent Schroedinger equation that can help to predict the future. I promised to myself to type it in good font every year, but always postponed. So when we were solving time dependent Schroedinger equation, we believed in separation of variables. And we did agree that this time-dependent part is nothing but accumulation of phase linear in time, and this phase comes into an imaginary exponential that gives this spiral helix, right? And time-independent part gets, when you go capital X, is those eigenstates of time-dependent part. So here is a little thing from the differential equations. Zane, Jared, are you taking or were taking differential equations in the past?
I haven't taken it yet.
Okay, now Zane, you will instruct all of us. So if you were seeing in these differential equations in the course the difference between general and partial solution, did you have this? Yeah. Can you tell your impression or something about it?
General impression, general equation can be solved. It's the more general form of it. So you have e to the x.
Solution, not the equation, but solution of the differential equation.
So it's a more general and then a more precise one, where you have a constant, not very much. Right?
And partial?
It's a kind of, you just differentiate half of it, right?
Okay, you didn't tell anything wrong, which is good. Yeah, thank you. I'll bring a little bit more to this. So, if we multiply this eigen state by this oscillating exponential, and we need to then this product of time dependent and space dependent part will be a solution of time dependent Schroedinger equation. Now, if we select different number n, like n plus 1, and compose the product, will it be a solution as well? Yes. Yeah. Everyone agrees? No one objects? Now, if we take solution where this number is n, and solution where this number is n plus 1, and add them together, will the summation of solutions be a solution of the same differential equation? Say yes. Yes. So it is, again, I'm not a mathematician and we are not in math class, but it is, if you go through this instructions in differential equation, there will be a theorem. So that for linear equations, adding sum of solutions is also a solution. And it is really cool. We use it in physical chemistry and quantum theory for the principle of superposition. We were already using it when we superimpose traveling waves. One traveling wave is solution, another traveling wave is solution, and their summation is also a solution. Make sense? Yes. Good. So if we put this one times this one, and then different number, this one and this one, their summation will be a solution. And now, at which percent, if we multiply one solution by weighting factor, we take like 10% of the solution number n and 90% of solution number m. Will it be solution as well? Not 50-50, but we will mix them disproportionately. Still solution. Yes. Now we have ambiguity. We can select any proportion between these basic solutions and it still will be a solution. Then how can we describe real life? Anything we compose out of these things in any proportion will be a solution. Which one will be true? So this is a main question for today's meeting. And I will not answer it right now, just memorize it and try to think. And if you have steam to think, try to find some associations and which proportion between the solutions will correspond to real life. And going back to differential equations, the summation of the solutions with unknown proportions, which I call C sub m and C sub n up front, is general solution. So if you, in general, it is correct. And if I select specific values for these coefficients to match realistic experiment, then you will be partial solution. So it agrees with what you were discussing, just more details. Okay. We already discussed it. Now, a little note on scalar products. So if this is a little building block that we will use as well. if we have a two-dimensional geometry, we can multiply vectors and get numbers, scalar product, right? By adding together like first component of the first vector times first component of the second vector plus second component of the first vector, second of the second, right? If they are 90 degrees, it will be 0. If they are parallel and the length is 1, it will be 1. No, everyone is happy. Now, the same idea can be applied to functions, which has not 2, but infinite number of dimensions. And just as an example, just to be quick, I'll just show it rather than, but you all can derive it. If you take function like constant and linear. Now, analog of scalar product is multiplication of products of functions. So you multiply them and integrate in certain limits. And if we do it correctly, it will be 0. Because these two functions are orthogonal, same as vectors at 90 degrees. Make sense? And here I do not like derivations, but especially if one can do it graphically. So a linear function going linearly constant, and if one multiplies it, it will be triangle with plus, triangle with minus, and they are equal in area, so integral is 0. Right? So it is an analog of scalar product for functions. Or we also call it delta function. Okay, so what are we going to do? Can you read this abbreviation? What does it mean?
Time-dependent Schroedinger equation, time-independent Schroedinger equation.
Excellent, excellent. Thank you. So we are adding together the eigenfunctions multiplied by this phase accumulation. And we are adding all of them. Like if there is an infinite number of solutions, we need to put all of them. So our sandbox has a lot of toys, building blocks. And in order to set up right proportions, we multiply each of these elementary solutions by expansion coefficient C sub k. So summation of this all the ck squared added together should give 100%. So the main question for today is how to select values of C sub k in order to match the wave function that we observed or post or set up in the past, or in other way. If you do know wave function at some specific time in the past, out of this information, we can, without ambiguities, define expansion coefficients. And again, we are not in the math, we are not going to prove it, but it is proved. If one plug in time equals 0 into here, then one will reproduce the same solution. Okay. Yeah, there is. I was in previous years, I thought that if I will write everything I say in with handwriting, it will have a hypnotic action on the class, and everyone will memorize and believe in it. So here is what we are practicing. We are practicing this partial solution by selecting C sub k, eigenfunctions, eigenvalues, and expansion coefficients, which we will know. And our wave functions are orthogonal. And now, if we set up time equals 0 in this solution, then the exponential to the power 0 becomes what?
1.
Yes, correct. So we just remove it. So wave function at time 0 is equal to summation of the all eigenstates times expansion coefficients. So if we believe in these theorems about general partial solutions, we just follow simple logic. Now, in this last line, I'm going to draw a logical connection about this ugly handwriting 5 word came from. So before they were inserted. What is bad about this lower line? The component, the variable, the thing that we need to find is t sub k, and it is in some it's on the right part, and it is not isolated. So we need to transform this equation into the form where it will be c sub k equals something, right? And this c sub k is multiplied by, even if you have one physical dimension, each function has infinite number of degrees of freedom, right? So we need to get rid of this phi sub k of x function. Now, how can we get rid of a function in equation? Oh, of course, we can take a razor and erase it, but it will be not mathematically correct. How can we correctly keep the equation correct, keep some imprint, some properties of this equation, but remove the wave function?
Set it equal to 0?
No, we need to, well, then it will be a very, very partial example only at a certain point, but and we want to keep the properties over the whole space. And the prompt is provided at the top of the slide, this handwriting. So if you have wave function phi sub n, and you multiply it by phi sub m, and then integrate, it will convert either into 0 or 1, right? Make sense? I hope that it makes sense for the online part of the class as well. And now what we are going to do is to multiply left and right part of the bottom equation on the another eigenstate of the time independential equation, phi sub m with a star, phi sub m with a star, and then integrate. Then in the right part, we will swap orders and multiply and integrate left and right. And then we will get rid of the product of the wave function. It will be either 0 or 1. On the left side, we do not have exact answer what it will be, but it will be just our protocol, our recipe what to do. So it is just the same stuff that it was before. So before we had only blue thing, and now we have the pink multiplier. So integrated by phi with different index. So let me entertain yourself and myself so that I write something instead of just showing slides. So integral phi m star psi dx equals integral phi m star dx somewhere, and here we have summation psi m phi m. So one can put swap order and just put integral in front of here, and then we will have summation n c sub n integral phi m star phi m dx here integral phi m star psi dx. So this integration of eigenstates of the Schrödinger equation will be either 0 or 1. 0 or 1, right? And there is a special mathematical symbol that, so it will be 0 if m equals n, and 1 not equal, and 1 if m equals n. So this symbol is often referred to as Kronecker delta. So this delta with two indices is like matrix with ones on the main diagonal and zeros everywhere, and it means it is an object that becomes 1 if indices coincide, 0 if it doesn't coincide. Just matrix with ones on the diagonal. So then this integral phi star m psi dx equals summation. So it will be C1 divided with times delta 1 comma n plus C2 delta 2 comma n plus C sub n delta n comma n plus C sub infinity delta and continue. So the delta functions of all terms except when the indices coincide, when argument of delta function is the same, it will be 1, right? And everywhere else it will be 0, right? So we can remove and keep. And this one will be 1. So we will have just C sub n. And basically it is an answer. So C sub n equals integral should be m here. Should be m. So C sub m equals multiplication of the eigenstate number m on the wave function at time 0 and integrate. And here are the words that one can say if you want to impress your colleagues in the future. So the initial wave function psi is expanded over the basis of eigenstates of time independent Schrödinger equation. So by this, same as we do vectors in two-dimensional, we can project one vector into another one. Now we project this wave function psi onto basis of this eigenstates phi sub n. And expansion coefficients, those are projections. So we go from continuous wave function to discrete set of projections. Make sense? Okay. There should be, yeah, okay. So it is the same thing that we did. Put C sub k up front. Here we have this integral, and then it is a way how I was memorizing what to do if one has summation of delta functions. So we do have summation n C sub n delta m comma n. So the delta is like a mouse or rabbit, and the summation is like snake. And when they see each other, they cancel, and we get only stuff between them evaluated at the value m equals n. Okay. And we already went over it. Here is the same thing. Just if anyone on the line or in class was hesitant to ask a question, I will repeat this basic derivation once again. So if we do have summation of all the delta functions, it means we are adding together zeros, zeros, 1, and zeros, right? So it will pick up from the sequence only one number when the indices are equal. The answer will be 1. If we plug in the expansion coefficient here, it will be a sequence of this expansion coefficients times 0, times 0, times 0, and only one will be multiplied by 1. So from the sequence, we pick only one element. And we get this element. So expansion coefficient is equal to integration of the slice of the wave function times eigenstate. And depending on which number we need, we put here different eigenfunction. Okay. So basically, well, please do not leave. Maybe I will check if I have more slides. But basically, we did everything. So we agreed that by theorems from differential equations, that linear equations have a general solution as a superposition of this elementary solutions. And in our case, it will be eigenstates of the time-independent equations times time-dependent phase of evolution. It should be energy, not multiplier. And our main goal for today's meeting was to find at which proportions this time-dependent and space-dependent elementary solutions enter into general solutions that match realistic situation. So this is defined by specific values of the C's of k coefficients, and they are found by expanding the wave function of the past times 0 over basis of all eigenstates. So it is the third way to predict future announced at the beginning of the meeting. From past to the future. From past to the future. I don't know if I can add anything more. Maybe just paint with different colors. So first way, second way, and third way. So let's put a bet that next slide will be announcing of the end of the meeting. Yes. So we are done. Everyone is welcome to leave